It's a very classical problem in fluid mechanics to look at the flow that occurs when you have two parallel plates that are considered to be very long and very wide, and one of the plates is moving. For example, here we see that the top plate is moving to the right with a constant velocity, with a constant speed v naught. And even when we looked at this problem earlier, we already drew some conclusions, mainly based on experimental observation, but we know that if we're talking about a Newtonian fluid, which is what we are interested in anyways, the fluid in the gap here is a Newtonian fluid, we know that there is a linear relationship between the shear stress in the fluid and the strain rate, which we know is given by the partial derivative in this case of u with respect to y, because it is such a simple flow field. And what we did then, because we didn't know exactly what this velocity profile looked like, is we said, well, let's assume that it's linear. And if it's linear or nearly linear, then of course I can approximate the derivative, partial u with respect to y, as the velocity of the top plate divided by the width of the gap between the plates. What we're going to do now when we formally look at this flow, including the viscous effect, is to find out that indeed, if the fluid is Newtonian, this profile is linear. So our assumption that it was linear was actually correct. Now, the other thing to recall is when we put all the forces into the momentum equation, I told you, because we didn't really go into the details of the derivation because it's lengthy, and it isn't really much different from the one that we did for the pressure forces, was that the viscous force per unit volume that will appear in Newton's second law is given by the divergence of this so-called shear stress tensor. And you don't really need to know too much about it, except you can go back and look at the notes and see exactly what this tensor looked like. But it is a 3x3 matrix where you have all the components of the stress tensor arranged in this 3x3 matrix. So we left it pretty much there, except that I told you what that term would look like if the fluid is Newtonian. So, but if we put it into our expression, then we ended up with this. So the so-called momentum equation for a fluid, which is, again, nothing but Newton's second law, written per unit volume, was this. So far in the course we have utilized this equation, but without this term, without the viscous term. So now we're going to put it back in there. Recall, for example, that if I don't have this term, there is a way, for example, that you can get Bernoulli's equation out of what is left, if this is out. But if we put this back in, then the story changes a little bit, because the effect of viscous forces needs to be taken into account. Now, what I did after that is I showed you what this equation looks like for a Newtonian fluid. So let me just put that in here. So that very same equation, if I write it for a Newtonian fluid that has constant viscosity, the equation that I get is the one here in the box. So again, the pressure term is the same, the gravitational term is the same, the acceleration term is the same, but I have now replaced this divergence of tau with mu, which is the viscosity, times the Laplacian of the velocity. And that's, if you remember, what is known as the Navier-Stokes equation. So the Navier-Stokes equation, also referred to as the momentum equation, is nothing but an expression of Newton's second law for a fluid, for a Newtonian fluid, which is deforming and moving. So that's going to be then our starting point today, this equation that we had seen before. So if we put all the terms, so let's now go here and put all of these terms and put a name actually to each one of them. I don't think I need that one anymore. So that same equation is written down here, except that I have broken up the acceleration into its components. Everything else is the same. So pressure term, gravitational term, viscous forces, and now the right-hand side is separated into the two components of the acceleration. So here you have the names of all the terms, of course. Everything is per unit volume. So this is the pressure force per unit volume, negative gradient of pressure. Rho g is the weight per unit volume. The new term for us is this viscous force per unit volume, and the acceleration, which is broken down into local and convective. So this is the Navier-Stokes equation, and it is a vector equation. So each term in this equation is a vector. And therefore, when we're solving problems, we typically have to write each of the components of this equation. So we write, suppose we were solving a problem in Cartesian coordinates, then we have the x component, the y component, and the z component. And sometimes that's why people refer to this equation in plural, let's say Navier-Stokes equations, because you're really talking about the three components. So suppose I do that. Suppose I say, well, let me write this equation in components. And therefore, if I look at the x direction, then I may have to zoom in a little bit on this. So it's a little, you can see it a little better. So there is the x component of the equation. And you have the original equation back here, so you can refer to each term and see exactly where it came from. Notice that one thing that I did is, because it is common to write this equation with the acceleration on the left-hand side as opposed to the forces. We're used to writing Newton's second law, F equals ma. But in fluid mechanics, we write the acceleration on the left-hand side and we put the forces on the right-hand side. So here's the acceleration on the left side. And again, it's separated into local, partial u, partial t, and convective, these three terms. Remember, this is only the x direction, so one component of the equation. And then on the right-hand side, I have the same forces that I had above. So the component of the gradient of pressure in the x direction is partial p, partial x. The component of rho g in the x direction would be rho gx, because I could have the gravitational acceleration in an arbitrary direction. It doesn't really have to be lined up, although many times we do line it up with one of the coordinates. But in general, it will be some component in the x direction. And then the viscous force. So notice that what I did is I replaced the velocity as a vector in the equation with the component u. And that's why, and I circled it in red so that you could see exactly where I made the substitutions. Wherever a vector v appeared, I replaced it with a u. Of course, you have to be careful with the convective acceleration because that's a little bit different. So remember, the convective acceleration has 9 terms, 3 in each direction. So the 3 that are in the x direction are written here. So that's my x direction component of the Navier-Stokes equation. And that's the equation that we are going to solve for the problem that we're going to look at today. And I would also have to write an equation for the other 2 directions, so the y direction and the z direction. But that's easy, because once you have the equation, say, in the x direction, what you need to do is just to write it in the y direction. You replace the circle u's that you have in this equation with lowercase v for the component of velocity in the y direction. I didn't write it out because it's really similar. And then if you want to write the equation in the z direction, then you just use w instead of u in the equation above. All right? Again, remember, be careful, because in the convective terms, you don't touch this u, v, and w that appear there. Those remain the same. That's why I didn't circle them. That's in the convective terms. All right. So now let's see, can we solve a problem using these equations? And in fact, can we solve our problem of the flow in a gap between two parallel plates. So let's say that we want to do that, and that's our first solution. That will be our first solution. It is what we call in fluid mechanics a co-ed flow. So this is the representation of the co-ed flow. There are my two parallel plates. I have put them a distance of 2h apart. Notice that on purpose, I'm making the separation 2h instead of h. The reason for that is that I'm going to put the coordinate system in the midplane of the gap. So rather than putting the origin at the bottom plate, I am putting it halfway up. And that's why the gap is 2h. So in terms of the y-coordinate, the gap goes from h plus h at the top plate to minus h at the bottom plate. I'm also lining up the acceleration of gravity with the y direction. So I'm putting the y direction in the gravity in the negative y direction. And then here on the right-hand side are the assumptions that I'm going to make as I try to solve the problem. And all of these assumptions then turn the problem in what is known as a co-ed flow. Right? So first of all, steady. We're going to assume that the flow is steady. There is no time dependence. We're going to assume, as I said at the beginning, that these plates are very large in both the x direction and, of course, the z direction, which is normal to the paper. And if the plates are very large in the x direction, then the conclusion from that assumption is that there should be no derivatives of velocity in the x direction. The velocity doesn't depend on the x direction because these plates are so large that whatever happens at some value of x will happen also at some other value of x. There is no influence from the end of the plates either at the far left-hand side or the far right-hand side. That's what we call a fully developed flow in fluid mechanics. It's fully developed. That's an important, let's write it here. Fully developed. Meaning that there is no effect of the entrance into the space. Right? It's so far ahead that we don't even see it. The next assumption is to assume that the velocity is only in the x direction, right? Because one plate is moving in the x direction. Right? There is no reason to expect that there will be another velocity other than the u velocity. So the v component and the w component are 0. That would not be true if we were not in the fully developed region. So if we actually were near the inlet, the beginning of these two plates, then there would be a velocity normal to the plates. But we don't deal with that because we're far from the entrance. We want to make the problem as simple as possible. We will assume it is incompressible, so rho is constant. And of course, I said that I'm putting gravity in the negative y direction. So those are my assumptions. So now I want to know what happens if I go to my equations and look at each term one by one and see what's going on. First thing we do, of course, is we look at the conservation of mass equation, our continuity equation. So remember, what's the continuity equation if the flow is incompressible? Divergence of v equals 0. So divergence of velocity is equal to 0, and there is the divergence of the velocity. Partial u partial x plus partial v partial y plus partial w partial z. And you can see, and that of course is equal to 0. Divergence of v is equal to 0. But because of all the assumptions that I made, each one of these terms is 0. Starting from the right, I said there is no w, I said there is no v, and I said that the velocity doesn't depend on the x coordinate. So each of the terms is equal to 0. And therefore the equation is said to be satisfied. I do get 0 because 0 plus 0 plus 0 gives me 0. If you want to think about the meaning of these things, of course, what's partial u partial x? What is the physical meaning of partial u partial x? It's a strain rate, right? What is the physical meaning of partial u partial x? Linear deformation of the horizontal side. That is correct. Partial u partial x is the linear deformation of a horizontal side. So if I draw a fluid element in here at some arbitrary position, partial u partial x tells me that the horizontal side, say for example the bottom side of this element, doesn't stretch or shrink. It stays the same. Partial v partial y would be the strain rate or the deformation of the vertical side, right? So if partial v partial y is 0, then the vertical side is 0. So this is telling me, also, even though it's all telling me that conservation of mass is satisfied, is also telling me that there is no linear deformation of this fluid element. All right. Let's see what happens to the momentum equation. So let me see if it still fits here. It might be kind of big. But let's just take a quick look at it right here. It does fit in there. So is that still there? Yep. So what happens to this equation? Let's first go here and look each term at a time and see what happens. So partial u partial t is 0 because I'm assuming that it is steady. U partial x, 0 because I just said that velocity doesn't depend on x. V partial u partial y, 0 because v is 0, and the same goes for the last term here, w is 0. So what I see is that all of the acceleration terms are 0. So I also learned that the fluid element that I drew here is not accelerating. Is it moving? Yeah, it's moving, but it's not accelerating. We already learned that it's not linearly deforming, right? Okay, so, and then what about the right-hand side? The first term on the right-hand side is the pressure force per unit volume in the x direction, partial p partial x. What I'm going to say in this first approach to the problem is to say that it is 0. That is, I'm saying that the pressure, if I look at this channel, the pressure is the same at any location in the x direction. There's no variation of that pressure. Okay, and then what else? Because I put the gravity in the y direction, this is 0. So it looks like the only thing that is left is precisely the viscous term that I want to take into account. So if I write all of that down here, that's what I have. Bunch of zeros, because everything is gone. And then the only term that is left, which is the viscous term, is now mu, second derivative of u with respect to y squared. What about the equation in the y direction? Remember, the equation in the y direction looks just like this one, but instead of a u inside the red circles, I would have a v, right? But v is 0. So these 4 terms are 0 on the left-hand side. Then here I have partial p partial y. That's the variation of pressure in the y direction. The gravity will be fully in that direction, rho g y, but that's now negative, right? Negative rho g. And what about the viscous term in the y direction? 0, because that u on the right-hand side there is now a v. So that's 0. So the only thing that is left in the y direction is that. Right? Notice how I flip the sign of the rho g because my g is in the negative y direction. And that's all I have left. So if I solve these equations, I can get the answer that I'm looking for, which is what is the velocity profile. You can see that the y direction, there is no velocity in it. In fact, this is something that we have seen before. What equation is that? minus partial p partial y minus rho g equals 0. Where have we seen that equation before? Huh? No, there's no velocity there. There's no velocity. Loud? Somebody said it over here. Hydrostatics. It is hydrostatics. So, back to chapter 2. Right? By the way, the z momentum equation, there's nothing in it. I don't even have to consider it because every term in the z momentum equation is gone. Of course, because I'm representing the problem as a two-dimensional problem. So if I solve the y momentum equation, then I get the result that we got when we were looking at hydrostatics, that the pressure is negative rho gy plus some constant. That simply states the fact that the pressure increases as you go down, right? As y goes more and more negative, the pressure increases due to the gravitational field. So this is just hydrostatics. There's nothing new there. The new one for us is the x momentum equation. This one right here, that is telling us mu partial second derivative of u with respect to y squared is equal to 0. What does that mean? What is the solution of that equation? Well, I can make this equal to 0 if I make the viscosity 0. If I set mu to 0, I'm done. But of course, that's not the case that I want to look at because that would put me back into potential flow theory. Right? So I have to rule out that case. I don't want mu to be 0. And therefore, my only choice is to make the other term that appear there, right? The second derivative equal to 0. And what does that mean? If the second derivative of u with respect to y is 0.
It's linear.
It's linear. Everybody see that? Second derivative equal to 0 means no curvature, right? No curvature. Second derivative is the curvature. So it's a linear profile, which of course I can get if I simply integrate that equation twice. So if I integrate it twice, I get a linear profile, which is what we had assumed when we looked at this problem a long time ago. It's a linear profile. How do I find these constants C1 and C2? There are no initial conditions because the problem is steady. Right? Initial refers to time. So no initial conditions. Boundary conditions is the right name, right? Boundary conditions. I have conditions at the boundary. What are the conditions at the boundary? At the walls. In name. No slip conditions. I have to apply no slip conditions at the bottom and the top. And of course, that means that if I apply them at the bottom plate is located at y equals minus h, is not moving. So the velocity has to be 0. And the top plate, when y is equal to h, also no slip condition means that the fluid has to move with the velocity of the plate at that location. So at the top, the boundary condition is u equals u naught. All right? So that allows me to find the constants. And I get that profile. I get that the velocity is a linear profile, which is given by this expression. U naught over 2, parenthesis, y over h plus 1. That is nothing but the profile that we drew here a long time ago. Right? That's that profile. It's a linear profile. You can verify it in that expression. If you plug in y equals minus h, you get 0. If you plug in y equals h, you get u naught. Well, I call it v naught in the drawing here, but this v naught is the same as that u naught. So let's just change this to a u naught. All right. So that's that profile. And the problem is pretty much done. I verified that a Newtonian fluid in a gap such as the one created when I have two parallel plates with one plate moving is a linear profile and satisfies the equation including the viscous term. So this is expected. Now, what else could I be interested in? It's written right here at the bottom. I might be interested in the shear stress because, for example, I want to find out, this could be a way in which I could measure the viscosity of a fluid by putting it in a gap like that. If I measure the force at which I have to pull the plate, right? If I measure the force at which I have to pull the plate, I can back out the viscosity of the fluid. So what is the shear stress? Well, we know that it is equal to tau. That's a little bit too big. Tau is equal to mu partial u partial y. So if I get partial u partial y from this equation at the top, partial u partial y, of course, is just u naught over 2h multiplied times mu. That's the shear stress. And what I notice when I get the shear stress is that it's the same across the gap. So if I am thinking not only of the plates, top and bottom plates, but I'm thinking about the layers of fluid, the successive layers of fluid as I go from the bottom to the top, each one of those layers is exposed to the same shear stress. Doesn't matter where you are in the gap because the result came out independent of y. There's obviously the velocity was linear, the derivative of the velocity will be a constant. So this is the same across the gap. All right, so now that I have the shear stress, I could find the force. How do I find the force? For example, if I want to know the force that I need to pull the top plate with, how do I get that force? Multiplied by the area of the plate. So I would actually need to know the dimensions of the plate. Or in other words, this is a force per unit area on the top plate. So if I could measure that force, then I can get the viscosity. All right, any questions before I add one complication to the problem? Or one more level of difficulty? Yes? Okay, from here, right? This is the Laplacian of u. What's the Laplacian? Let's write it right here. What's the Laplacian of u? Let me throw that question back at you. That might be why you don't know what's happening. What's the Laplacian of u? The Laplacian, remember, is the sum of the second derivatives in each of the directions. Right? That's the definition of the Laplacian in 3D. Right? But for us, this was 0, because there is no variation of the velocity with y. This was 0. So the only term left is that. Right? I'm sorry. The first one is 0. We said that the velocity didn't depend on x. The last one is 0. The only one left is partial second derivative of u with respect to y. So that's how I go from here, from this one to this one, right? In other words, I only have one term of the Laplacian left, right? Which is that one. Any other questions? Okay, so now let's throw in one other feature. Suppose that I change the problem a little bit, and I now keep both plates fixed. You don't see the plates. Suppose I keep both plates fixed. How do I make the fluid move? Parabolic. Parabolic. How do I make a fluid move parabolically? Oh. How do I make it? This is a practical question. In practice, how do I make the fluid move if I have the two plates fixed? Pressure difference, right? Put a pressure difference. So let's do the following. Okay? Almost the same problem, but now it's going to be a pressure-driven flow. The plates will be fixed. So all I'm going to do is I'm going to add a pressure gradient in the x direction. Remember, when I set up the problem, I said I'm not going to have a pressure gradient. I'm going to say that the pressure is the same everywhere in the x direction. Now I'm going to say that I'm going to have a constant pressure gradient in the x direction. So the pressure is not the same. It changes with x, right? But it changes linearly because I'm saying that dp dx is a constant. dp dx would be the slope of that. So what changes in the problem if I do that? Again, this doesn't change the conservation of mass equation, so I'm repeating that result from before. The continuity equation is satisfied. What about the momentum equation? If you go back and take another look at the equation and bring back any terms that we may have dropped out before, the only one is precisely the one that we're adding. Because in the previous version of the problem, we said there was no pressure gradient, and that's the only thing we have. But now I put it back in there because I want to have a pressure gradient in the flow. So I put that term back. The y momentum doesn't change. You would agree with me. If I look at the previous y momentum equation, it's the same. I'm not making any changes there. So I still have that hydrostatic pressure variation in the y direction, same what I had before. But now if I take this equation and I write it like you see here in the box, then that's what the equation that I'm trying to solve. And again, always think back of the previous case. In the previous case, there was no pressure gradient, and therefore this was equal to 0. That's why we got the linear profile. So now I'm getting that the second derivative of u, the second partial of u with respect to y squared, is equal to 1 over mu partial p partial x. But I'm saying that this is constant. That this pressure gradient is a constant. Right, we said that above, right there. So what is this new profile going to look like? Now is when you can say your word. Parabolic. Right? Because if I now solve this equation, the second derivative of u with respect to y squared equals to a constant. What is u? A parabola, because now it has curvature, which you can get, of course, by integrating. So if you integrate that equation twice, you get a parabola. And the same question that we had before, how do I find these constants? C1 and C2. Same way I found them before. Right? I find my constants from my boundary conditions, which are the same as before. I didn't change those. So I still have my no slip conditions to satisfy. Right? So I can plug them in and find those constants. And what do we get? So I put those in there. Here I'm evaluating the expression that I got at each of the boundaries, right, at minus h and plus h, and putting this time that the velocity is 0. So that's what allows me to find C1 and C2. Again, it's just algebra from that point on. You find that C1 is actually 0, the first constant that multiplied the linear term. And the second one is given by that expression. So now that I have C1 and C2, I can clean up the result and put it there. So indeed, it is a parabola. So now the velocity profile looks like this parabola in the red box. What does that look like in the actual space between the cavity, between the plates? So here's the top plate, here's the bottom plate. They're fixed. But if I draw the velocity at some x location, I get that, you don't see that, I get a parabola. Right? That's what the profile tells me. So it's a different problem. The plates are fixed. I have a constant pressure gradient, and I get a velocity profile that looks like a parabola, that it is a parabola. And this is the equation for the parabola. Again, you can verify that it satisfies the no-slip conditions because that's how we got the constant. So if I plug in y equals h or minus h, in both cases, the quantity in parentheses is 0. And I get 0 velocity at the two plates, at the two walls. But that's what the profile looks like. And I could also find, if I want to find the shear stress, I can do that. So suppose, what do I need to do to hold those plates in place? Then I can find that force if I find the shear stress like we did before. Before we do that, however, where is the maximum velocity? It has to be at the center. And remember, the center is at y equals 0, because that's where we put the origin. So when y is equal to 0, you get the velocity at the center. Minus 1 over 2 mu partial p partial x h squared. That's the maximum velocity at the center of that channel. Right? Why is it negative there? No. Who is saying that? You again. This is deja vu. So why is that? Right? If the pressure decreases, not the gradient, but the pressure, right? If the pressure decreases from left to right, right? If the pressure is dropping from left to right, that means that partial p partial x is negative, which makes this maximum velocity positive, so it would go to the right. So the negative is there because of the sign of the pressure gradient. If the pressure is increasing from left to right, right? Increasing as I go from left to right, then dp dx is positive, this stays negative, and the flow would be to the left. So that's the reason for that sign. It just drives the fluid in the direction opposite to the increase in pressure. Yes? Okay, and then the last part was what I told you. I can also find the stress, again, by finding the first derivative, the shear strain rate, partial u, partial y, from my parabolic expression above there. From this expression at the top, I can differentiate it, get the partial of u with respect to y, plug it in there, and get that expression for the shear stress, this one here. And what I notice is now it is not constant. Do you remember in the other case, we said the shear stress is the same for every layer of fluid in the gap. That's not the case anymore. You can see how the shear stress depends on y. It's different for each value of y. Now at the walls, at the top and bottom walls, plus y equals plus h or y equals minus h, it is of course the same magnitude, it has the same value. And the shear stress, another thing to note is, what is the shear stress at the very center? The very center of the gap is when y is equal to 0. I get, if I plug in y equal to 0, I get tau equals 0. Why is that? Why is it that the shear stress is 0 right on the midplane? No. Remember, it's the slope of the velocity profile. And that slope happens to be 0 right there. Right? Remember, when you're thinking of the slope, you have to think about plotting velocity versus, right? Velocity versus distance. So the slope is 0 at the center. Now we look at the profiles like that, right? But that slope is 0. Right? So there is no shear stress at the very middle plane of the gap. Okay, any questions? before we do one more thing? No questions? Okay, what is the thing that I can do next? What do you think it is? What if I have both problems at the same time? Right? So suppose I have the gap, like we just did. So here is the two plates. And now I have both conditions happening at the same time. So I have a pressure gradient, which is not zero in the gap, but I also move the top wall with a velocity u0. So I do both problems in one. I have the motion of the top plate and a pressure gradient. How do I solve this problem? How do you think we solve this problem? Huh? Huh? Same way. Can I do something without having to solve them? Superposition. Why can I do superposition? Why is it that I can do superposition? Which we did already, for example, when we were looking at the inviscid problems and we were dealing with the velocity potential, which satisfies Laplace's equation, you might recall. We could add solutions because we're solving a linear equation, which is Laplace's equation. But what about now? This is the equation that we are solving. If we bring it back here, not that one. Okay. This equation in the red box is the question we just solved. So the difference between the first and the second problem, in the first problem, the right-hand side was 0. In the second problem, the right-hand side was a constant. Right? And of course, we had a different boundary condition at the top, either a moving plate or a non-moving plate. But what about this equation? Is it linear or non-linear? Non-linear, why? Because that's a good guess?
Because there's the pressure doesn't have is it going to make it non-linear?
No, that is not correct. Remember that I know the pressure gradient because I'm imposing it. Right? I say I'm going to put a pressure gradient in there. So that's a constant. The right-hand side, think of it as a constant. This is a constant. Mu is a constant. The pressure gradient is a constant. That's a constant. Is that equation linear or non-linear? You still think it's non-linear? Huh? That equation is linear, right? Because what would make it linear or non-linear is whatever is happening on the other side, right? And the second derivative is a linear function, right? To make it non-linear, what would there have to be?
You'd have to have like a partial u, partial y as well.
Where?
On the left-hand side.
So adding? So as I add here on the left-hand side a partial u, partial y, does that make it non-linear? That's still linear. Or a partial u, partial y, like he's saying, but not adding, but multiplying. What makes a differential equation non-linear is if you have products of the function or its derivatives. Any product of the function and its derivative makes it non-linear. There's none such a thing here. This is completely linear. It's just one term and it's a second derivative. So because the equation is linear, if I want to look at the two problems at the same time, I just superimpose them. So I just take my first problem, which is the one on the left, and I add it to the one on the right. And the equation that I'm solving is the one there at the bottom. So if I do that, just having to adjust, of course, for the boundary conditions, but this is what we get. not surprising to us is the fact that what we get is a sum of the solutions. So if we combine them, remember this was the previous solution, the linear profile, and this is the one we just got for the pressure gradient. So I just have one solution on top of the other, or added to each other. One solution added to the other one. It's a simple combination. Okay, any other questions? Yes? What happens to the velocity profile? That is a very good question that I was hoping to address next time, but I'll give you a preview because you're asking. Because we don't really have time to go over all of the details. But there is a velocity profile for a flow that combines both the motion of the plate and the pressure gradient. But I'll go into the details of that next time because we're out of time. All right?